Wow. I only speak English. You too? A little bit? Okay. Well, this is nerve-wracking, but I'm so excited to be here. We had a long trip to get here. You are hiding at the end of Santiago, it seems like, but we're here. And yeah, so I have to say that there's no data in this talk, even though I collect a lot of data myself. I study the mind in experimental tasks. There's no data here, just ideas. So there, don't be disappointed at the end. This question, how to build a mind, is central to cognition. If we could build a mind like in, artificial intelligence, that would be amazing. That's what we're trying to do. And so I'm interested in that question, and I want to show you what I think about this. Good. So this is my question, right? So how to decide how to build a mind, we have to understand how to think of the mind. What is a model of cognition? And I give you a quick overview of my talk. This is so confusing to see myself as opposed to my slides, but I will manage. So the talk really has 3 parts, and the first are fun. I don't know if you know the word straw man or straw woman, like something we argue against. That's my favorite thing to do. I like showing what the problem is with others, not with myself. So we'll start with that, traditional models. And then we talk about the problem with the traditional model. And I'm going to refer to it as the rational mind fallacy. And then the third part, like I said, 3 parts, my proposal. And I'm arguing, just in case you want to hear the end of my talk, it's coming now. Oops, sorry. Here you go. I argue this, that cognition is an embedded network, EN. I made it up. We can call it other things, but I call it that, embedded network. And we're going to talk about this. This is animated. Why is this animated? This is amazing. Okay, so there'll be some duplicates here because I double animated here. Okay, very good. So we're going to talk about what are the necessary and sufficient features of the embodied network. How does it emerge? And can this approach explain cognition? I want to warn you, as I said, what I will not talk about is how to prove my points empirically. So there's no data. Or actually how to grow, how to build an embedded network. Or, this is really what I'm interested in, is how do we change an embodied network? How do we change a kid's beliefs? But I'm not going to talk about that here, so only those 3 parts that have a check mark. Okay, so do you remember part 1? We're going to talk about the straw man, okay? So stuff that's out there, the traditional model. And I don't know if you know this guy. His name is, like you see, Jeff Sachs. Anybody has heard of Jeff Sachs? No. He's very famous, more famous than me, much more famous than me. And I heard a talk of his not too long ago at the conference called Cognitive Science Conference. Maybe you heard of that. And he gave a talk, and it was very impressive. He's very good. He studies the brain and has a theory about the brain, and this slide showed up as an idea of what the brain might look like, or what the model of cognition might look like. So I was in that talk, and I took notes, and I couldn't quite write it down quickly. And I thought, okay, I'm going to ask him to send it to me. And he did. You know that expression, bless his heart? He was very nice, man. He sent me that thing, but I'm going to now criticize it, so that's very bad. But this is his model, and I think I can criticize it because he's famous and he can take it. And I also found the reference, and this is his model. So what does he say? He says this is a model of cognition. Well, there is the sensory processing right over there. So the input, comes through the senses, and then you make some prediction. That's his essence of his theory. He makes some predictions. The mind makes some predictions. Then it checks those predictions. See the error monitoring over there. And then when there is an error, when the prediction was wrong, then you check with other beliefs that you might have, event models, and then it affects how you process. So you might see this room, and I predict that you are going to like my talk, let's say, but at the end you might not like my talk. Then I go back to go like, I wonder why that is. Maybe it's English. So next time when I come into this room, I'd be like, oh, they're not going to like my talk. Okay, so you see that's pretty much the model of cognition. Makes a lot of sense. But I disagree, so we'll get to that. But first, the second straw man, in this case a woman. This is Jean Mandler. Do you guys know about Jean Mandler? She studies babies, also very famous. And I picked her. I could have picked a lot of people. A lot of people have a wrong cognitive model. I picked her because when I was in graduate school, this was a paper we read in class, and I just loved this title. Can you imagine? She had the guts to name her paper this, How to Build a Baby, as if we can build a baby. And she goes on and says, this is what you have to put in to get a baby. So I always wondered if one day I can give a talk with that title, which I do today. So I used her title for today's title, How to Build a Mind. So see, there's my title, How to Build a Mind. I stole it from her because she did it too, and she doesn't know. She's wrong anyways. What does she say? Okay, now the animation starts again. Okay, here's what she says. She says, again, the same question, where does knowledge come from? What is a good model of the mind? And she says this, simple, the mind is doing a perceptual analysis. That's her term. So she says these babies, I don't know if you guys have kids, but imagine, a 3-month-old or a 9-month-old is looking around and then analyzing the environment. And I'm going to read this for you. So it's a symbolic and conscious process by which one perception is actively compared to another. That's her idea, right? So rather than making predictions, she says these babies compare one perception with the other, and that's how they perceive, that's how they learn. She goes on to say it's an analytic process. It's doing conceptual thought. It's a conceptual kind of understanding rather than primitive recognition. Now, here's where they're both wrong. This is now my second part. We already made it to my second part of the talk. I call it the rational mind fallacy. And I looked online. Nobody has had this fallacy, so I'm going to name it. It's the rational mind fallacy. For both of these models, the guy Sachs and then Mandler, they make this assumption that the mind is rational. You see that first line over there? At the center of the cognitive model is a rational mind, or a rational analysis. Remember Sachs had that error monitoring thing, that checks if you're right or wrong, and that was the essence of his model. And Mandler proposed this perceptual analysis, these kinds of comparisons. They're very rational. That's like the baby sitting there going like, I wonder how this compares, or doing these error analysis. Oh, I predicted this, I should have predicted that, I got it wrong. So that's the rational mind. And as I said, I could have picked many more models. Piaget, maybe you heard of Piaget, he's big in kind of, cognitive development. He's dead now, but he was big in cognitive development. And he had this idea of formal reasoning. So formal means smart. means, you know, logical connections, rational. So can you imagine Piaget, you know, he was in Switzerland. He was French, but he sat in this Swiss chateaus and was thinking about how does the mind work? And because he was so smart, he thought we're all so smart. And he developed this theory of development where the babies are not so smart, and then they get smarter, and then they get smarter, and when you're an adult, you have something called formal operational stage. You're very smart. So all these people make the same mistake. They assume the mind is smart, eventually at least. Mandler thinks babies are, Piaget thinks what adults are, Sachs thinks we're all along as we perceive. And I just don't think we do that. I mean, do you do that? Do you analyze everything rationally? Do you sit there and go like, oh, I predicted X, but Y turned out. I wonder how I have to fix it. You know, I don't do that. Maybe you do it, but I don't. So here are some examples of anti-rationality, when the mind actually is not rational at all, when the mind ignores the evidence. These are just some examples, but they're big. Let me read them to you. Perceptual illusions, that's kind of a non-rational mind. Stereotypes, superstitions, attitudes, mistaken beliefs, risk-taking behavior. This is just these are just examples of when we don't show a rational mind. I'm sure you've all seen it, you know, when you look at kids or adults and they do these things and you're like, oh, you're crazy. You're not rational. I think that's more common. And it's not just a clumsy fluke. It's not like, oh, oops, they're just not smart enough or they have to learn more. Look at this book that I found. This is an American book, The 7 Laws of Magical Thinking, How Irrationality Makes Us Happy, Healthy, and Sane. So what are they claiming here? That this irrational behavior is actually a good thing. Superstitions are good, and attitudes are good, and mistaken beliefs are good. So it's not just a clumsy fluke, it's the essence of the mind. That's what I'm saying, right? So it's not a rational mind. But I'm going to call it the mind is unruly. Unruly is a word in English. I didn't know it. And I put a bunch of examples of what else it could mean. Disorderly, rowdy, wild, unmanageable, uncontrollable, disobedient, ill-behaved, and so on. I don't have to read all of it. But I think it's kind of funny that they have all these words for unruly. I mean, my claim in essence is that is a better description of the mind than the rational mind that Sachs assumes to be the case, or Mandler or Piaget. And so therefore, this is the question. We need to find a viable model of cognition that can explain that unruly mind. That's what I'm trying to do. Okay, let me give you some examples of the unruly mind. This is a classical task in cognitive development. It's called the A not B error. Do I get a sense? Have you heard of the A not B error? Maybe, maybe not. Okay, so this is, Piaget invented this, and he, as I said, he started the whole area of cognitive development, and this was one of his tasks. It's very, very robust. It's called the A not B error because a baby, see that baby, is put in front of two locations, and we'll refer to the first location as A and the second location as B. That's where A not B comes from. So you see a toy is being hidden under location A in front of the baby, and the baby, you see on the second picture, finds the toy. This is a fun task for the babies. The toy gets hidden, and then right in front of the baby, and the baby wants to get it. And then the toy gets hidden again at the same location, location A, and the baby wants to get it, and so on. So a few trials at location A, but then on the third picture, the experimenter, Piaget, you know, again in his French chateau or Swiss chateau, changes and puts the toy to location B. And then the baby does not actually go to look for the object at location B. So that's where A, not B, is the error that the baby makes. The baby goes to A, not to B. That's the A, not B task, and we typically interpret this as the baby's just stupid, really. The baby just doesn't get it. The baby doesn't have an object concept or something. For years, I mean, this is how this task is interpreted. But maybe, maybe not. Maybe what looks like a childish mistake is instead a signature feature of the mind. It's that unruliness I was telling you about. There is perseveration, which is a good thing. It's the stickiness between experiences. This kid learns something. As the baby reaches to A, there is some learning going on, namely to expect the toy at A. And there is a resistance to perturbations. All of these things are good things. Perseveration, perseverating in the same task against challenges, it's a good thing. Learning is a good thing. Resisting perturbations is a good thing. So this is an example of an unruly mind rather than just not a very smart kid. And in fact, this is fairly recent data that came out of the University of Indiana, where they showed that, and I can't quite reach, but imagine from the picture 3, right over there, right there, picture 3 to picture 4, imagine right between when the toy was hidden and the baby can reach, right between that, between picture 3 and 4, the baby is just briefly lifted, like you see on this picture here, just briefly lifted like that. See that? And the error disappears. Well, how can the error disappear just from a brief lift? It's not that this baby all of a sudden gets smart from being lifted for a second. So we cannot traditionally explain this particular finding, and that's why I give you this example as the unruly mind. It's not the dumb child. The mind just does things that are unexpected and almost like they're on their own, in their own world. I'm going to skip to this example because well, it's kind of interesting. No, I'm going to skip to it because I want to get out of here. I need to tell you anyways. If we miss the train tonight because of this example, I'll be very mad. But I'll tell you anyways, another example of the mind doing crazy things, being unruly. That's the argument, right? This is an old study, Carmilov Smith and Inhelder. Carmilov Smith was a collaborator of Piaget, so they worked together. And they found, there's a particular finding that they published. Actually, it was Inhelder, Bärbel Inhelder, who worked with Piaget, sorry. They gave kids, these are toddlers, they gave them these beams to balance. And so you have 3 predictions. I'm going to need you to answer this, okay? So listen up. What do children do? They either can do it, right? Or they can't do it. Or they can do it first. No, they can't do it first and then they get better. Any guesses? Is it 1, 2, or 3? 3? Okay. Any other guesses? So it turns out, actually, that they can do it at first, but then they make mistakes and they look really stupid. The mistakes are idiotic. And so it's another example of this unruly mind. What happened? How is it possible that the mind gets it right? But where is the error monitoring kicking in that then leads to bad performance and then the baby sticks with it? So that's all I'm going to say about this. But I hope I have convinced you, oh yeah, we don't need that. I hope I have to convince you that the existing models assume a rational mind and the mind is not rational. So sometimes, of course, it is, but like you guys sit here and you're thinking very hard, but you have to also explain the non-rational mind in a viable model, and that's what I'm trying to do. And as I said, this is my argument. Cognition is an embedded network. So networks have been studied many times. Maybe you guys study networks. It's been studied in biology. It's been studied in physics. it's an up-and-coming field, and there are many different kinds of networks. Here I just show you 3 of them. They have names, but I don't need to go in there. And I'm not the expert on networks. There's actually another set. Here's another set of networks. These are small world networks, random networks, redundant networks. Every network has their name, and a lot of people study it. And I know nothing really about networks, but about embedded networks. And that's one special kind. And that's the kind that you find in the environment. So Ramon is going to be bored because I showed this picture yesterday too, but you guys have not seen it. This is an embedded network. It's an ecosystem. It's an ecosystem from that describes an area in the US that's called the Cone Springs. You see here a picture of it. It's very sparse, which is why you can actually study it. And what you see here is how calories move. See, plants provide calories for detritus. That's just organic material that's being what is the word? It's decomposed, you know, material that's getting decomposed. And then bacteria feed of it, but then also bacteria get decomposed over time. You see those 2 arrows up. And then bacteria feed detritivores. Those are worms. So worms eat bacteria. And they also eat organic material. You see those 2 arrows. And then carnivores, like birds will eat worms, and then when birds die, they'll turn into organic material. This thing here is the network I'm talking about. This is an example of an embedded network. And I'm arguing that that's what the mind looks like, okay? So that's cognition. We don't need this. I don't know why it's there. So this is, imagine this is the mind. And that little thing is nothing, right? So don't worry about that. So this is an embedded network. It's just a schematic, and hopefully for the rest of the talk I can explain to you what is meant with these lines and the squares. It's also called, this is not animated, some people call it adaptive representational network. I like that name too. But the main thing is that it's self-sustaining. It can sustain itself, just like the animals living in the Cone Springs. It's self-regulating, like it has ways of adjusting. If one doesn't work, if there's too much cold, then it will just adjust itself within the network. And it's emergent, meaning there was nothing there before. It just emerged, you know, the cone spring. Nobody would go try to find the essence of a cone spring ecosystem. It's pretty obvious. It just emerged. All right, and the main thing is the network of the mind is composed of components. You see those, A, B, C, and D. And it has these 2 forces, or these 2 parts. Network sensitivity, that's the dark lines. I don't know if you can see them. And network cohesion. And those are the lines between the squares. Let me give you a little more meat on this very abstract theory. So let's compare and contrast first, okay? So the top picture was Sachs' model. Remember, he uses it to explain how we perceive events, how we create meaning when we perceive events. And this is the ecosystem of the Cone Springs. So where is the difference? You see, all of them have components, and all of them have lines that link. What is the essence? What is the difference between traditional model and embedded model? I'm going to give you a minute to think about this, but I'll help you. See, I redrew that initial model, just a little more schematic. So those 4 things you can think of, there's something, a unit responsible for perception. There's a unit responsible for creativity, that's the prediction part. There's a unit responsible for error monitoring, and there's a unit responsible for memory. So that top thing is the same thing that Sachs said, just with slightly different words. because I want to highlight how common his model actually is. All models in cognition today have that kind of structure. I'll show it to you in a different way. See, this is again Sachs' model, just with different colors and arranged differently. See, there's the perception. We think of perception to be first, right? And then there's some creativity happening. We make predictions or we make guesses. And then we check those with the error monitoring system. And then there is memory, of course. We have schemas, we have concepts, and all of it feeds together. What's the difference? Oh, and I gave you this picture here too. So this is my question, okay? What's the difference between what looks like a network above and this network that's down here? See, this is just the same thing I told you before, but now with pictures. There's the decomposing grass. It feeds the bacteria. The bacteria can turn into organic material. The worms feed off the bacteria and the decomposed grass and other organic material, and the birds feed off the worms. So what's the difference between the traditional model of a network and the embedded network? Any suggestions? It looks the same, doesn't it? Do you see any differences?
The arrows are in both directions?
Yeah, but the errors are in both directions there too, at one point, memory to perception. Yeah, so there's more interconnectivity, right? So that's good. But probably Sachs would imagine that it could be connected. Maybe my prediction could affect my perception, and maybe my error could affect my perception, But so you're right, it's more interconnected, but more. What else?
In the second model,
Yeah.
every unit
Yeah.
is open to the environment.
Exactly. That is the crucial difference. And that's where the word embedded comes from. It's embedded as a whole. It's not something separate. See, Sachs and Mandler and Piaget and all the traditional models of cognition assume that it happens inside somehow without continuous input. An ecosystem, all components are embedded, more or less. Some are more embedded than others, but they all have the opportunity to be embedded. That's the difference. So that alone, let's see if my animation works here, that makes it so it can be self-sustaining. Because if the input over here breaks down, let's say it's a cold winter and it's not that much grass that year, the whole system is not going to break down. There is some way in which it can still sustain itself because there's input here. The birds will, whatever. I mean, it won't last forever, of course. It is dependent on the outside, but it has different entry points. It's embedded. And so that's the big difference. Both systems are more or less self-regulating. That's when you see arrows in both directions. They have this feed forward and feed backward system. But only this second one can be truly emergent. And this is the problem with traditional models. They cannot tell you how it got there. How did a baby develop an error monitoring system unless it was already there? How does the baby develop a memory unit unless it was already there? But in an ecosystem, well, how do you develop worms unless they were there? No, worms just emerge. If the context is just right, the worms will emerge because they evolve to feed off the bacteria, and the bacteria evolve to feed the worms. It's interrelated. So these two networks, they look very much the same, but they are intensely different. And I want to point out the kind of compare and contrast because I think we often fool ourselves with traditional models to think, oh no, it is a network. We study connectionist models, for example, And that's a network, but it's not. It's not embedded. It just has one entry point, and everything else has to live off that one entry point. And that means the minute you cut off that entry point, how does it continue on, you know? So I'm going to tell you just a little bit more about how it emerges. So remember, my question is, what are the primitives? Okay, what do you need to develop a mind? So these are our ideas. Imagine each perception, each sensation creates an experience. That seems easy enough. Like a snapshot. Maybe people sometimes talk about it as synchronization. We don't have to go there. The main part is this. They become the components of the network because, this is why, each experience has a very brief afterlife. So there is a snapshot, but it doesn't immediately disappear. It just stays on for 1 second longer. And then the next one that comes in connects with the previous one. It synchronizes, like fireflies or, you know, school of fish. So the synchrony, the initial snapshot, lasts a moment longer than the outside that gave rise to it. And then there is an overlap of experiences, and this overlap yields that synchrony of experiences. So, for example, if I see you guys now, and then the next second I see you again, and the next second I see you again, there is some continuity that overlaps, a similarity that stays the same, and that's the basis for that network. The connections between images will be on the basis of similarity from one moment to the next. And so I can even close my eyes and I still see you because it can sustain itself for a while and connect. And that synchrony is then the link between experiences. Okay. So to give you an example, or to apply this to the A not B error, remember, that's what the babies do. They see an object be hidden under A, and then the baby finds it under A. So you can imagine those components be those impressions of, or those momentary experiences, the toys being hidden at location A, the baby reaches at location A, the baby lifts the cover under A, and then there's the toy under A. And then again, the toy is hidden under A, the baby reaches for A, the baby lifts the cover under A, there's the toy under A. You see, these experiences will have something in common. It's a cycle of toys. And you don't see the arrows very well, but at each of these moments, the baby sees new things. It sees, it's actually kind of difficult for the baby to organize its movements. So the whole organization of movements creates an impression. The lifting of the cover creates an impression. Seeing the toy, another impression. And those link because they're similar. There's something similar. There's a toy and the movement and the happiness of seeing the object, and it links into this network. And then in phase 2, when the toy is hidden under B, there's only one part that gets perturbed. Everything else stays in place. The baby sees the object, but then there comes the arm. Oh, I remember the arm, and the arm already reaches at A, and so that gets strengthened and lift the cover. And so that arrow above, the minute it starts, it strengthens the entire network, and that's where you get perseveration. Okay, so what are the necessary features to build a baby? What are the primitives of cognition? What do you need to build cognition? And if you don't believe me, I might be wrong about this, but what I'm trying to tell my students, think when you want to teach somebody something, think of something as complicated as trying to grow a rainforest. We forget how complicated that can be. We kind of assume, oh, I just tell you, 3 plus 2 is 5. Come on, can't you get it? Well, you're trying to grow a whole rainforest. But what do you need? You need these 4 things. Outside order, a medium that's sensitive to outside order. Number 3 is the most interesting one. You need interruption of order, and you need a medium that's sensitive to order. And I think there's more here. Let me just see this real quick. Yep. I used to cover these, but I'm taking 1 minute to go through these. These are the 4 things that you need to build a baby. You need outside order. Obviously, 3 plus 2 has to be 5. There is some order that the baby has to learn. The toy hides in meaningful ways under location A. That order needs to be given. But then, and then of course you need a system that's sensitive to that order. The perceptual system is sensitive to light. The acoustic system is sensitive to, acoustic waves. This is the interesting part. To grow this network, to grow a rainforest, you need those meaningful interruptions. I can't prove it to you yet, so you just have to take me at face value. But if there is no interruption of order, if, for example, you have a climate where everything stays the same at all times, you get a very shallow ecosystem, a very easily perturbable ecosystem. It's only once you have those interruptions of the winter and the dark that you get these networks that can outlast interruptions. So that's what it needs. Those 4 things. Kind of easy. Now, they're not all the same. So different networks are different. Yours is different than mine. In different situations, they change. They change dynamically. But only in 2 ways. So it's kind of easy to model when we ever get to model it. Networks differ in sensitivity, and they differ in cohesion. Remember, sensitivity is how much sensitivity is to the outside, those dark arrows, and cohesion is how much do those yellow arrows, how much are they connected. I don't need to go to the explanations, maybe because you understood it. Now, there is much, much more to say, but this is almost my last slide. I just give you some ideas of what all this could mean. For example, sensitivity is like attention, and cohesion is like memory. Now, if you go to cognitive science conferences, the people who do attention will be in room A, and the people who do memory, they'll be at the other way of the hallway. Have you seen that? They don't mix. They're either people studying attention. What are you studying? Attention. Okay, then this is where you give a talk, or you study working memory, or long-term memory or whatever, and then there you give the talk. We don't know how to bridge that divide. People in memory say, oh, of course it matters what you pay attention to, but we're only going to study how you memorize it. And then people in attention say, of course it matters what you believe, but we're only going to look at how you look at stuff, attention. So the network model allows you to put the 2 things together. Sensitivity and cohesion are natural parts of the exact same network. And it's kind of a nice combination of very different fields in cognitive science. So sensitivity is responsible for fluidity and change, the ability to discover new things, the ability to listen and be, attentive. Cohesion, on the other hand, is responsible for stability and perseveration. So again, in cognitive science, people either study the fluidity, the dynamics, the plasticity of the mind, or the plasticity of the brain. Maybe you heard it. And there's an entire field that studies just that. And then on the other hand, you have the stability, the memory. This embedded network idea allows you to think of both as connected. You can't think of just one without the other. Cohesion explains all the phenomena that deal with ability to sustain yourself against perturbation, like the A not B error. That's cohesion. Anything where a kid holds on to a belief, holds on to an attitude, holds on to a stereotype, all of those things can be understood under cohesion. It's also responsible for blindly ignoring the evidence. So it's also responsible for what we see as irrational when people don't learn. I don't know if you follow the American elections. Yesterday there was a debate. Did you see the debate? Do you follow the debate? It's crazy. But people, it seems like one camp tells the other one, how do you not see? How do you not understand what I'm telling you? Did you not see the data? and the other camp says the exact same thing. How do you not see the data? And you're like, and I just talked at the airport with somebody again, and he says again, I can't believe it. My brother, he's so smart, but he doesn't seem to understand it. So there's a lot of kind of heat. Why? We're dealing with attitudes. Attitudes, once they're established, they have high cohesion. And once high cohesion is part of the system, part of the network, it will resist perturbations. It's very nature, and sometimes even valid perturbations. You can't distinguish between valid and invalid perturbations because you're holding on to your system. Same with ecosystems, those dinosaurs did not see it coming and they died out. They were not sensitive enough to a decrease in sunlight, and they're like, oh no, it's going to be fine, it's just a little perturbation, boom, they're dead. So that was not very smart. Okay, there's much more, as I said. This is not as interesting, but sensitivity is a function of outside order. When you see kids being able to learn about statistical patterns, language, they're very, very good language learners. Well, you can explain it with sensitivity. A sensitive system can learn statistical order. This is where the interruption of order comes in, and I'm not going to spend much more time on it, but just this, that cohesion actually forms as the outside order is interrupted. And next time when I come, hopefully I have more to convince you of this, but that's maybe the most controversial point. Yeah, I'm not going to spend any time on that now. And then different contexts require different networks. So in other words, if you are sitting here going like, okay, which one is the best network? Is the best network the high sensitivity network, or is the best network the high cohesion network? Well, different contexts require different things. So there's no such thing as the best network. Yesterday I gave a talk and this guy says, wow, but we want kids to be more sensitive to the truth. We want them to learn. Well, in some contexts that's a good idea, but in other contexts you can just confuse the kids and it's not a good idea. So it's not one size fits all. For example, for learning the language, you need a very sensitive model. For learning math, you need a very cohesive model, and that cohesion is very difficult to build in the context of math, which is why we have math problems. Finally, and this is the main point, embedded network can explain the unruly mind. It can explain both being smart and sensitive to environment and ignoring the environment at the same time in one model with two parameters. That's kind of amazing. Okay. Of course, I have to be right, too. But let me get to the sum. So this is what I argued for. Cognition is this embedded network, like an ecosystem. We talked about what the necessary and sufficient features are. Remember, you need order and interruption of order, as well as a medium that's sensitive to order, and as well as sensitive to interruption of order. And the components need to actually be sensitive to each other, like water molecules. Water is a good example of an embedded network. How does it emerge? All we need is synchrony. Synchrony is a very well-studied phenomenon in life, so it can explain a lot of different emergence of species, behavior of different species, and that's all we need is synchronization. That's kind of amazing. You don't need a memory system. You don't need the error monitoring system. You just need a system that's sensitive to each other and the outside and be able to synchronize. And can it explain cognition? So we're saying yes, but we don't know how to prove this empirically or how to grow a specific embodied network yet. We want to. We study math learning and science learning, and we want to put that knowledge into the kids' heads, and it's not as easy. Of course, and we don't know how to change an embodied network yet. Okay, that's the end of my talk. Thank you.
Thanks, Heidi, for such a nice talk. Could you exemplify your network using the A not B experiment? What is going on there? There is cohesion, and so that's why the child sticks and then there is a Could you unfold it? Yeah, yeah. By using your...
Yeah, so I remember the main thing between this kind of network, the embedded network, and a more traditional network are those arrows that you can't see here. They're dark, but you see the ones that come from above. So the baby doesn't just perceive where the object is hidden and then builds everything in their mind, but the baby perceives where the object is hidden, and then the baby perceives the movement. And the babies at this age are young enough that the movement takes quite a bit of effort. So the aiming takes a lot of like, wow, what's happening here? Oh, cool, I'm reaching. So of course with adults, that is not a big impression. So for adults, this network would shrink. Adults wouldn't go like, wow, I'm reaching, oh, cool, there's A. But for babies, these impressions are amazing. So each time, each second of this event creates an impression. That's the main point. So, and because the baby creates these 4 impressions here, where the toy is hidden, the movement, the kind of fine-grained movement, which is complicated for babies, but they can do it. They just about can do it. Creates another impression. And then finding the toy is like, oh my God, a toy. So it creates these 4 impressions. So that's what's different from how it was explained before. Before, we assumed the baby just sees the object, and then everything else happens in the mind. The reaching, the finding, that's nothing. And then the object, new object again. So remember the Sachs model, the baby just perceives the object and not all the rest. But once you add these 4 impressions, they connect because the toy is over there, so the baby will see the toy, so there's going to be continuous impressions of the toy, or the location at least, and then my hand reaches there, so there's some similarity, some synchronization between those impressions. And then, so these arrows that you see there, going up, back and forth, that's a synchrony. Now they're not the same impressions, but they're synchronized, they go together. The baby will stare at that location, and then there comes the arm, and there's a synchrony. And once there's a synchrony, it will outlast the event. And then it goes on, then the baby lifts that hidden, that cover, and then finds the toy. So these impressions all synchronize together, and the synchrony is just like the calorie exchange and the cone springs. Now it doesn't exchange calories, but it synchronizes. You can even think of species synchronizing with each other, but we know a little more about how they do it. They eat each other. And that synchrony lasts on, just like fireflies. Once they start flashing in the same rhythm, it will last on. So it lasts on past when a new event happens, you only have one tiny little perturbation of the entire network. See, the rest still stays the same. There's still a kind of body memory to reach. And this is why, and I forgot to say this, when you lift the baby, what's happening when you lift the baby? The whole thing disappears. Now the lifting is new. It doesn't fit to anything. See, there's no, the lifting of the baby is not a perturbation. It just breaks the entire system apart. Also because these babies, their motor coordination is so new still that the lifting just takes apart those bodily connections. The reaching is now not there anymore because the baby was lifted. So the A hiding error or the A hiding event creates this entire network that then lasts outside of that little perturbation of showing a B hiding event. But when you lift the baby, because the system is so heavily built on motor behavior, when you lift the baby, the motor memory, so to speak, is gone. The impressions are now new, and the baby will find the object because now it's going to be only that memory of that event. It's a lot of hand waving. So don't feel badly if this is kind of silly, but it's it's how we explain it. There's, by the way, I don't know if you know Linda Smith in Indiana. I mean, they did that experiment with the lifting of the baby, and they have a model that's very similar. So it has to do with activation. So you activate these different parts, the motor and so on, and it does the same. Yeah, we have to stop. Okay, so does that help at all?
Yeah, so
5 minutes more.
thank you.
Yep. Thank you. First, thank you very much for your presentation.
Thank you.
You didn't go into neuronal,
Right.
let alone molecular level of
Right,
the cognition.
right.
So in your explanation, you talk about impressions and synchrony as a primitives,
Right.
items of this. So I wonder if you're arguing about certain autonomy of the mental, of the psychological level, or you are thinking that is entire grounded in biological,
Right.
ecological level?
So the answer is B.
Mm.
Yeah, so it goes throughout life. So it's on the level of neurons, it's on the level of cells. Same system of synchrony is the basis of all life, and therefore also of the mind and making sense. You know, somehow biologists know that. They have studied synchrony for a long, long time, and they know that cells have a kind of synchronic system that keeps cells alive, and, you know, ecosystems, of course, and species and so on. But when we come to understanding the mind, somehow we got caught on the computer metaphor, which is not synchronous. So machines do not have synchrony. And then we caused all kinds of problems with that. But yes, definitely. So everything emergent has the basis of synchrony.
So this is heuristics.
It's just a metaphor at this point. Yeah. Right.
Thank you very much.
Yeah.
You said, okay, it's fairly clear that this is important. The system is kind of open to the environment and kind of regulate itself.
Yeah.
And it's easy to I don't know, to follow that kind of
Right.
reasoning. What is not so easy for me to follow is the necessary and sufficient condition. You said that it was 3 or 4.
4.
And can you argue? It's kind of a strong statement.
Yeah,
that
it is,
they are
I know.
necessary and sufficient.
That's right.
So, and can you please elaborate a little bit more about it?
Well, what else do you think we need? That's all you need. I couldn't come up with more. That's what you need. You need order and a system that's sensitive to the order, but as long as it can synchronize with it, that's enough. And then it needs a medium that's sensitive to itself. And I'll give you another example, but I don't have time because they want me to leave. But I can't think of what else we need. And then you need interruptions. We haven't talked about much of that, but that comes from, you know, the idea of thermodynamics and the movement towards, you know, greater entropy and things like that. And then you need a system that's sensitive to that. You need nothing else for life to happen, and therefore you need nothing else for the mind to happen. I'm going to say one sentence with a few commas, but it's only one sentence. If you take water, water is a physical system. Water is sensitive to the outside, right? So it's sensitive to heat, for example, because it's based on movement, on the basis of heat. And water has a lot of properties, like an embedded network, like a tornado, for example. A tornado is a system that stays itself. The only problem with the water compared to the mind is the water molecules are not, their afterlife is short. If a water molecule moves this direction, it will not keep moving if the heat changes. So it's too sensitive. It has very little cohesion. The mind has more cohesion. That's the only difference. Can you imagine? We're just water. Water with a little bit of more cohesion. I can't think of anything else. Maybe next year I will, but if you come up with something we need, then write me.
One question was about when you talk about when the order is interrupted or the order is, what to say, is interrupted, where the interruption come from. I thought in your model probably the missing part is the people who is taking care of this baby. In your model is the missing part looks like the social part. the interaction with other people. I thought maybe they are in some part. I thought maybe the people who is interacting with this baby are coming, or they are generating this interruption in the order.
So I told you the part that is most controversial, I think, about this talk is that you need interruption of order.
In a systematical way?
That it doesn't have to be systematic, but it has to be an interruption that the system is sensitive to. So take again the ecosystem, an interruption in warmth, the system is going to be sensitive to. It's sensitive to temperature, or water. An interruption in water is going to, the system is going to be sensitive to. It doesn't have to be irregular. It just has to be an interruption. And that one, I'm pretty sure it's needed, but I'm not ready to convince you yet. So there I can't answer that. But the question of the social interactions, see, I think what we define as a system is arbitrary. They're hierarchical systems. We could do the exact same analysis with a social system. The interactions between people have the exact same property. We can connect, we can exchange, we can synchronize, we can be sensitive to others, like families, for example, could be an embedded network. In this particular task, we defined the system entirely mentally, and there's no interactions with others, but we could have drawn a system over a social system. So it's arbitrary. Okay. I know we have to go, but this was lovely. You guys are a good crowd. Thank you.
Well.